Hello, everybody. I hope you're having a great day. The beginning part of Chapter 8 deals a lot with creating equations for periodic functions. And so those will usually be sine or cosine graphs. And there's almost always more than one way to write the equations for these functions. And they can be done as a sine graph or a cosine graph. They both usually work. You just have to put in different parameters depending on whether you're using sine or cosine. So I've got three examples here to work through with you, and hopefully that'll help you get ready for the problems that are in 8.1.2. So number one, we have temperature fluctuations throughout the year, or actually throughout a day. And so it says the temperature can be modeled by a sinusoidal function. Now the term sinusoidal, that doesn't mean we have to use a sine function. Both sine and cosine are sinusoidal graphs. They both have the same shape. So that shape of the graph where you have a graph that goes up and down like this, that's called sinusoidal. So it can be done with sine or cosine. And it says the high temperature of 105 occurs at 5 p.m. and the average temperature for the day is 85 degrees. Okay, and so in a day there are 24 hours. So if we on my graph paper, I'll let each line represent 1 hour. Okay, so 5 p.m. There's noon. And there's 5 p.m. So it reaches its high of 105 at 5 p.m. So let's say this is 105. And it says the average temperature for the day is 85 degrees. So if we put our midline here at 85 degrees, that's our average temperature. And so the temperature is going to fluctuate above and below this midline. And so they didn't give us any information in this problem about what the period is, but it makes sense that the period is 1 day. We're going to complete one full sine wave in 1 day. And so if the period is one full day, then it's going to take, if we think about a normal sine graph or a cosine graph, so we have a high, starts high, and then goes low from there. And so the distance between the low and the high is half the period, because this is normally 2 pi, and so the distance between the high and the low is half of that. That's only 1 pi. And so in this graph, the period is 24 hours, so half the period is 12 hours. So if we go 12 hours to the left, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that's where we'd expect it to be at its low value. And so since this is 20 degrees above the midline, this is going to be 20 degrees below the midline. And so that puts us at 65 degrees for our low. And so we have our low and our high, and this is 5 a.m. And so it's at its low at 5 a.m. and it's at its high at 5 p.m. Halfway between the two, let's see, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1, 2, 3, 4, 5, 6. So at 7 at 11 a.m., it's going to be right at its midline, because that's halfway between. It's 6 hours here, 6 hours here. And so we kind of have an idea of what our sinusoidal curve looks like now. There's the high and the low. So if I go another 6 hours this way, 1, 2, 3, 4, 5, 6, it'll be back at its midline again. So that would be at 11 p.m. It's going to be back at its midline. And then if I go 6 hours from this point, 1, 2, 3, 4, 5, 6, it's going to be at its midline. And so now we have one full cycle of this function graphed. We don't see a full day yet because we haven't gotten to 12 p.m. but or to midnight, but we could. That's only one more hour, so it's going to be a little bit below the midline at 12 p.m. So we have some idea of what this graph looks like now, and so we need to write the equation based on everything that we know. So we see that our amplitude is 20 because our midline is at 85. We go up to 105 and down to 65. So our amplitude is 20. So I'm going to make this a sine graph, because here's a sine graph crosses its midline normally at the origin. So a normal sine graph would start at the origin. I'll show you how we can do that. We'll do this problem both ways, so that we can see the multiple answers that we could get. So if I do this as a sine graph, I see that this point was shifted left 1 hour, and and it's also an upside down sine graph. So I'm going to write y equals 20 sine. Now for our period is always 2 pi over b. And so we know our period is 24 hours. And so that means b has to be 12 over pi. Or sorry, pi over 12. And so we're going to have pi over 12 x plus 1 because it was shifted left 1 hour. And then the midline is at 85, so it's up 85. So that's one possible way to write the equation of this graph. And another way to write it as a cosine graph would be if we took this point as our high point. By the way, I need to fix one thing here. Since it was an upside down sine graph, I'm going to say it's negative 20. Okay. Now, if I take this point as my high point, cosine graphs start at their high point, so I could also write this as y equals positive 20 cosine. In this case, it's been shifted to the right. That high point has been shifted to the right by 17 hours. So x minus 17. We need to put the period in there, so that's b is pi over 12, and then shifted to the right 17 hours, and then again shifted up 85 because our midline is at 85. So there's another possible equation that we could write. And another way to do this, if we take this point as our starting point shifted, we can say it used to be here, shifted over 11 hours. That would be a sine graph. So y equals positive 20 sine of x minus 11 pi over 12 times x minus 11 plus 85. And so we've got three different equations that all produce the same graph. And that's assuming that we did all that correctly. And so now we're trying to figure out what is the temperature at 9 a.m. And so we should get the same answer from all three of those if we plug in 9 for x. So the first one, let's make sure we're in radian mode. -20 sine of pi over 12 times, we're plugging in 9 for x, so 9 plus 1 plus 85 gives us an answer of 75 degrees. Okay, and let's try it with the next answer that we got. So this one would be +20 cosine of pi over 12 times 9 minus 17 plus 85. Same answer, 75. The third option, 20 sine of pi over 12 x minus 11, so 9 minus 11 plus 85. So all three of those give us the same answer. Normally you would just come up with one answer, but I just wanted to show that there are multiple ways of doing these problems using sine or cosine, depending on where you know, if you know where your high points are or your low points are or where your midline points are, you can decide whether you want to use a sine graph or a cosine graph. But in all cases, we come up with a prediction of 75 degrees at 9 a.m. Okay, problem number 2 is very similar. So what I'd like you to do is pause your video and try problem number 2 and press play when you're ready to see the solution. And so for example 2, we have a high temperature of 84 degrees at 6 p.m. So this is 6 p.m., which would be x equals 18 because we're adding 12 hours. At noon, noon would be x equals 12, and then 6 hours later would be x equals 18. And that's where it has its high temperature of 84. So we can say that's up here at about 84. The average temperature is 70. So if we say that's 70, that's 14 degrees. 84 is 14 degrees above the midline. So that tells us our amplitude is 14. So if we go 14 degrees in the other direction, that puts us at 56. So from 56 to 70 is 14 degrees, and from 70 to 84 is 14 degrees. And for this one again, since it's 24 hours, the distance from the high to the low is going to be 12 hours. So if I go 12 hours backwards, that puts me at 6 a.m. 6 a.m. is going to be the low point. If I pick the point in the middle, 6 hours between the two, that's where it's at its midline. And then 6 hours to the left, 1, 2, 3, 4, 5, 6. So now it's at its midline again. And so this one would look like this. And that would be midnight. Okay, so this one we can do without shifting at all. So this one's a little bit easier because the midline, the starting point here and the ending point landed right on the 0-hour mark and the 24-hour mark, and so we didn't have to shift this. If we do it as a sine graph, all we have to do is make it negative because it's an upside down sine graph. So our solution for this one would be y equals 14, negative 14 sine of pi over 12 x plus 70. So there's our equation, and so it says find the temperature at 7 a.m. and so at 7 a.m. if we plug in 7, we have 14 sine of pi over 12 times 7 plus 70. Putting that in the calculator, negative 14 sine of pi divided by 12 times 7 plus 70. We get about 56.5 degrees. And that looks reasonable on our graph because at 7 a.m. it's just a little bit warmer than it was at 6 a.m., which is 56 degrees at 6 a.m. And our third problem, we'll do this one together, is a Ferris wheel problem. So imagine we have a Ferris wheel that you can imagine being at one point on that Ferris wheel, and it's just going to keep going around and around and around. And so the height of a person riding the Ferris wheel is going to go up and down as the Ferris wheel spins. And so it says that it's a 20-foot diameter, which means it's a 10-foot radius. People are boarded at a platform that is 2 meters above the ground. The wheel completes, okay. Okay, so if we consider that they're boarding at the lowest point, that is 2 feet above the ground. And so that puts our midline at 10 plus 2, which would be 12. And so the lowest a person ever is at 2 feet, and the highest a person ever is would be way up here at the top, which would be 22 feet. And so this is 0, this is 2, and this is 22. And so our midline is at 12. And so we know that our equation then is going to have an amplitude of 20. Okay, so they're starting low. So let's sketch what the graph would look like. So they board at 2. That's where they start. And then the 6 o'clock position on the Ferris wheel is level with the loading platform. So that's where I had it originally. The wheel completes 1 full revolution in 6 minutes. So that means the period equals 6, and period is always 2 pi over b. So 2 pi over b is 6, which means b is pi over 3. And so now we have b, we have our amplitude, and it starts low and then goes to its midline and then to its high and then back to its midline and then to its low. And so 1 full cycle takes 1 minute or 60 seconds. And so we can write this as a cosine graph, flipped upside down. Our midline would be here at 12. And so y equals, our amplitude we said is, amplitude should be 10. I think I originally said 20, but it should be 10, and it's an upside down cosine graph. So negative 10 cosine. We said b is pi over 3. It hasn't been shifted at all, so it's just going to be pi over 3x, and it's vertically shifted up 12. So that is the equation that models our function. How much of the ride in minutes and seconds is spent above 13 meters? And so it might be helpful to model this on the graphing calculator. And so if we put in y equals negative 10 cosine of pi x over 3 plus 12. Set our window. It does a full rotation in 1 minute, so full rotation in 6 minutes. And so we'll go 0 to 12. That'll give us 2 cycles. The highest y value is 22, so I'm going to go 25. Actually, this is a negative, so we'll go negative 2 up to 25. And then if we graph it, there's 2 full cycles riding the Ferris wheel. And so we want to know when is it higher than 13. So I'll graph y equals 13. And so we see this part of the graph is higher than 13. So we just need to find those 2 intersection points. And so I'll go second calc, intersect, blue curve, and it finds the intersection at 1.595 radians. And then we'll do it again to get the other intersection. And that's at 4.404. Okay, so if we subtract those two, .404 minus 1.595, we get a time interval of 2.809 minutes. And so to get the seconds, 0.809 times 60 is 40, we'll call it 49 seconds. So it's going to be 2 minutes, 49 seconds is the amount of time that you're above 13 feet in one rotation. And so those are the 3 examples for today. So you should be ready to now go ahead and try the problems that are in section 8.1.2 in your CPM pre-calculus book. Have a great day.